Okay, so now some examples of the visual entropy glyphs in potential uses. We've not tested these in user studies yet, but these are some examples of where we're going. The first one's the very beginnings of a collaboration. This is a mock-up of a search and rescue task where targets have been labelled with distance and certainty of them being human targets. And a search and rescue commander needs to decide which one to visit first. So we're going to try and test out a decision process in this environment. A second example is here. It's a plugin for Power BI that Mike Simpson wrote over last winter. And this allows us to take in data with two characteristics, value and uncertainty, or actually in this case it's showing an acceleration value, and plot that on a 2D graph, or actually over a city model. But here there are several things going on. The dots represent the number of COVID cases per day in either South Tyneside in the lower line or Newcastle in the upper series. The colour represents the number of cases per capita. The height represents the cumulative total number of cases to date. And the shape is representing the acceleration. So it's of interest to know if the outbreak is increasing, accelerating, or decelerating, slowing down. And so we tried to code that into this mock-up here. And this is the third and the last example we've got at the moment. How do you represent machine learning outcomes? So this is a system front end connected to some neural networks trained on the MNIST dataset. So the MNIST dataset is around 100,000 images of the characters from 0 to 9. And when you train the network, it can recognize, classify handwritten characters against this dataset. I can draw a handwritten digit in this panel here. I can select a network, and I'll select network 0, which is the least accurate of these networks, and ask the system to classify that digit for me. And it says here, you can see straight away, it thinks this is a 2 with high probability. So the scale of the glyphs here goes probability high to low, or uncertainty low to high. See, the terminology here is important. But beneath that is the direct probabilities for each digit, and you'll see that the network thinks that it's only very likely to be a 2 and not much else. If I clear this drawing, we can try a different one. We'll try 4. Hope you'll agree that's a 4. Ask the system to classify this. Again, it's classified it with high probability to be a 4. We'll try again. We'll do a 7. So 7s can be quite tricky. We'll see what happens. So it's classified it as a 7, but with as a 3, but with high probability. So that's for a human would clearly not make that mistake, but here the system does that, and machine learning systems do that quite a lot. Let's try a more accurate network, being designed and trained for longer. Okay, so network 2, which is more accurate, will indeed correctly classify with high certainty that this is a 7. We can kind of interrogate why it thinks that. So this is on the right, the image is fed into the network, and this is the areas of that image that most contributed to deciding that it was a 7. And you can see where there's a bright red spot or a white spot, that those roughly correspond to the 7 shape in the image. Okay, let's clear all. Let's see if we can recognize a 9. Back to network 0, and it's wrong, but in this case it's wrong with high uncertainty. So it's saying, well, okay, I think it might be a 1, but I'm not really that sure. So the probability here is actually one of the lowest down here, on the lower half of the graph. Okay, so that's how that works. The visual entropy glyphs are used to represent the output, the classification of the network, and the probability of the network doing that. And it's this kind of very direct, everyday representation of uncertainty and probability that we're interested in trying to get across to people. So finally, where are we going next? What are our questions and what directions? So we're very interested in a number of things here. One is language. When's it better to use images? When's it better to use words and numbers? When should you mix them both? I'm going to do some tests on this. And indeed, what is the language of uncertainty that might appeal more to the public and decision makers than the mathematical language that we'd want to present to them if they were mathematicians or statisticians? Acceptance is an interesting question. Can we, over time, make a language of uncertainty become more trustworthy to the public? Rather than talking about certainty and definite results in science, can we make it normal for scientific results to be uncertain? And then we can look at the levels of uncertainty and the range of uncertainty. And finally, the challenge that came out of the UK intelligence community is how can we represent and make decisions from multiple sources of uncertainty that are not directly compatible? And that's an interesting visual challenge because we need to be able to represent them in a way that human cognition can understand, even when there's no mathematical solution there. I'd just say Sherman Kent did some work on the language problem in 1960 or so. His report, Words of Estimated Probability, looked at whether you should use numbers or words in intelligence reports going up to high-level command. I believe he concluded that the analysts preferred numbers and the decision makers preferred written language. Okay, thank you for listening. You can catch me on Twitter, and thank you for everyone who's worked on the project in the last 2 years. Arzu at Northwestern University in Switzerland, and her colleagues who've run some of the trials for us. Sarah, Lucy, Mike and Kevin at Newcastle all contributed significantly to this. Andrew Woods at Curtin University and his Hive, where we've run some of the trials. And Susanna Soon at Curtin University, who's working with us on the search and rescue task. And for some patient advice on statistics, basic statistics, to David Firth at Warwick University.